Hello, we are going to review some of the basic ideas of impulse and momentum. So first thing to note is the basic definitions of things. You probably already know momentum is denoted by letter P, and because vector, put an arrow on top, and the definition is mass times velocity. V is the velocity and m is mass. The impulse is a little bit more complex definition, and we are going to do in a stepwise. So if you had a constant force and it acted for a time delta t, then their product is going to be an impulse. Now this is a vector, so by product we mean the magnitude of this will be multiplied by delta t, and the direction of j will be the same as the direction of f. Okay. If you have a force whose magnitude varies in time, and let's see is a function that's given that way, but whose direction is not changing. An example is like I have a baseball is being hit by a bat, so the force from the bat will be like this. So in that case, what you'd get is a direction of the impulse is the same as the direction of the force, because the direction is not changing, so it's the same. But the magnitude of the impulse will be obtained from the area under the curve. So your magnitude versus t, and you may get force like that, which is different amount at different time, and this is the area that's going to be the magnitude of, that's what we mean by area versus area under f. So this is called area under f, and because this magnitude, this area will be positive. Now if the direction is also changing and we are working with a single component, so say we are working with same definition will apply if we're working with say x component and it was varying all over the place like that, so sometimes positive, sometimes negative. So this will be this part will give a positive impulse, this part will give negative impulse, and this part will give positive impulse. So we'll have to add all of this to get j sub x. I won't get the full, I'll just get the x component of j if I'm working with the x component of the force. But the idea is the same, area under the curve. This is the area under the curve, and this is the area above the curve. The way under and above is this line, the zero force line. Okay. Second law of motion, when you work with second law of motion, usually think of F equals ma or F equals dp dt, but if you can write that in an impulse and change in momentum form. So if I look at the net impulse, so if you look at add up all the impulses, then you will get the change in the momentum, net momentum. So each force, say force 1 will cause its own change in momentum, and force 2 will cause its own change in momentum, and so on and so forth. So if I add up all the left side, that means I need to add up all the right side. The right side is basically the delta p net. So these are the things that are basic aspects of momentum and impulse. Now let's look at an example where you can apply this. So let's look at an example of a golf ball of mass say 46 grams. I looked it up. Now you hit with a club, and let's see the average force. When we say average force, That means we're thinking in terms of constant force. Average is winning mean constant. Even if it's not constant, somehow it has been averaged out as if it was a constant. So we can use this as a constant force. So we can go back to the constant force, this definition, and then we can just use product. Magnitude will be product magnitude there. So it's also said that the club was in contact for this. So this is the delta t. So this is how we say delta t. Information of delta t is given in this manner. When you're doing a integration or you're doing area under the curve, the delta t is spread out like that. And so it's a different, you can see the force, just multiplying with the force, you'll have a question which value of the force are multiplied. But in the average, you have a constant, just one force. But if you were to plot this, it will look like F, some average for time. This is t in milliseconds. It's going to be 0, 0.5, and this will be 4,000 Newton. So this area is the same thing as, you can see, just multiplying the force with the delta t. So the two definitions are consistent when they agree with each other. So we'll have the two information, direction of J same as direction of F, which is from club to ball, that direction. How about the magnitude? J is just F times delta t. So 4,000 times 0.5, 4,000 times 0.5, but this is in milliseconds. So I need to divide by 1,000 to convert that to a second. And so this 4 times half, so 2.0 Newton second. So that's the magnitude and that's the direction. So I've got both information done. So a question like this, what is the impulse of the force, does not really ask specifically to give you to say what's the direction and what's the magnitude. Because the impulse is a vector property, we need to specify both of these things to give a complete answer. Alright, if the ball was at rest, so this is saying that, okay, you have this much impulse, how much momentum has changed, right? So this, if speed change can be obtained by momentum, right? So it's an application of the second law of motion. So we'll say J net is equal to delta P net. And so magnitude is the same because the direction is constant here. So this can be in just terms of magnitude. So this, applying this will be, so I will have right side is P final minus P initial, as total mv final minus mv initial, and this is mass of the ball, and this is the speed of the ball, and this is set to be 0 here. So this becomes mass Pf minus 0, carrying on this over there, that becomes mass Pf here. So I can see that I can get this speed Vf simply by J net over n. I just make sure that I got the J net right. Well, when the ball was hit with a club, this force is the net force. Okay, so I can say that this is the thing found in A is J net, not just any J from one force, but it's just the net. There are gravity and the normal forces from the ground, they're kind of balanced, so they're during this time their impulse is 0. So I just have to work it out algebra now here. This is Newton second, and mass is given in grams, so I need to convert into kilogram. 0.46 kilogram divided by 1000, and so this one, I if I calculate this, it's about 44 meter per second. So this is the answer. Okay. We can do another example where we have to do the area under the curve. So here is a impulse for area under the curve. So a train is accelerating for 100 seconds, and then it decelerates. This accelerates and decelerates is given there just for the direction's sake. So when something accelerating, acceleration is pointed in the direction of the motion, and when something decelerating, acceleration is pointed opposite to the motion. So the force will be, if the train was going that way, for this side force is positive, it is the x-axis, and when decelerating over here, the acceleration is pointed that way, so this force will be negative. So if I take the x as the track, and we plot the x component of the force, I will see all these positive forces for the 100 seconds. And it's given that the force is not constant, force is actually changing. And at 100 seconds, suddenly the force becomes negative. Means it's something else, maybe brake or something applied, so force becomes negative, and then it's actually minus 500 Newton when I apply x component. So at t equals 0, at this instant, the train's momentum is given. We're not working with velocity right now or speed, just work with momentum directly. And we're supposed to find the momentum at this time, at this instant, and the momentum at this instant. Well, how do I do A? Well, assuming this is the net force, so this is the net force, okay? So because of net force, I can find the area under this curve, and that will give me the impulse, net impulse. So J net x, we're looking at the x force, so J net x, and is from 0 to 100 second interval, and that just gives me this triangle, so the base times height times half. So base is 100, and this is in seconds, 100, and this is 1000. So this just 50. So I got a 50,000. This is Newton second, and this must equal delta P net in the x direction. So which is Px final minus P of P final x and P initial x. So this one given to be that quantity. So I have a P final x minus 2000, and this unit is same as Newton times second, and that must equal to J net x, and that's equal to this number, correct? So this unit is same as that unit. So we can see that I can send 2000 on the other side, so P at the end final is the 100 second, so P at the 100 second mark and the x component is 52,000, and because we're using momentum, we can use the unit kilogram meter per second. So that's the answer for this. what's the answer about this? Well, we can go from the area from here all the way there, or we can just say, well, I already have this much momentum over here. We need to just get the area and do between here and here. So we can say P 120 seconds minus P at X, P 100 second X equal to J from 100 second to 120 second. That's X. So we need to find this, and this area is going to be negative. 500 times 20. So 500 times 20 Newton second. And that's equal to 10,000. So we already know this one is that. And when bring over here, then we have 52,000 minus 10,000. So P at 120 second X just will be equal to 42,000 kilogram meter per second. Okay, so these are two examples that should help you review other examples in the book. So, well, we'll stop here. Take care. Bye.